about me drawing out one of the hydrogens, just the one we're going to be using, and leaving the other two invisible? Do we feel kind of like, all right, yeah, we feel fine about that. Like as long as neither of the other two hydrogens do anything, we're good? Or is it like, just show me all of them, because why not? We got, okay, we seem good? Just one? Cool. So, we've arbitrarily decided, because I drew this hydrogen, that this one is going to end up being the nucleophile. It's not yet, but it will be once we deprotonate that, right? So, arbitrarily, equally arbitrarily, this guy is not going to get deprotonated and will be the electrophile, right there on the carbonyl carbon where we're used to it being. Let's take, oh, no, not yet. Let's take base, and I'm going to start drawing lone pairs because they help remind us how many electrons are already around things and where we can move things when we do resonance. We're going to have hydroxide steal that, that's an arrow, steal that acidic proton, and these electrons from that bond are going to go right there. I mean, or we could put them on the carbon, but that's ugly and crowded, so let's just go ahead and do what we always do. We are going to, I'll draw this guy later. Here. He can live up here, so we know that he exists from the start. We just don't care about him yet. Also existing. And we get that. Conveniently enough, we have an aldehyde, so we don't have to worry about this happening on both sides. On two different sides. So we've got this guy, and now let's bring in this guy that wanted us to know he existed earlier, but wasn't going to do anything. Because now, I drew him on the wrong side, but whatever. Now we've got a nucleophile and an electrophile, right? So the arrow is not going to come from the carbon, right? Because arrows have to come from a source of electrons. The carbon is our nucleophile. We're going to end up with a bond to that, but this carbon does technically have two little hydrogens attached to it. So it's not like it has lone pairs to start attacking things with, like oxygen or nitrogen, when we can draw directly from the atom. So we're going to start our arrow at the double bond, and we're going to take those pi electrons and attack the electrophilic carbonyl carbon. But how many bonds am I trying to make to this carbon right now? 5? One too many? So easy fix, bump those up there, and we get easy fix, and then we start drawing things that are like, they're both oriented this way, and now we have to combine them, and it's awkward and difficult. So let's do H. Well, okay, no, we're gonna make the H tiny. We're gonna draw this one. Yeah, we're gonna draw, wait, what if I do this? There. That's easier. Perfect. This helps. So now I can draw this. This has a negatively charged oxygen. It had a little H. It still has an H, but now I'm going to take this nicely separated bonding spot, and that's this guy, right? And I'm going to make our new bond to this guy, because basically what we did is we made new bond right there. Just so now it looks pretty. This guy is attached to, this is this one, right? Not the carbonyl carbon. So I'm not going to start drawing oxygens off of this. I'm going to go up to the carbonyl carbon here, and oh, you know what? This was a carbon with two single bonds and a double bond, and I took away its pi electrons. Am I gonna leave that carbon with 3 bonds around it, or is there something I can do to keep all our octet rules happier? Steal these guys, right? Wait, marker.
So you don't need to do that first before you use that double bond?
I'm correcting myself because I forgot.
Okay.
Yeah. So, I mean, as long as it's in this step,
Yeah.
you can forget like I do and correct yourself later. Just don't put it out. I mean, as long as you remember to keep everything consistent, I guess technically you could leave this off and do this, and you would have a positively charged carbon here and a negatively charged oxygen, right? So if you didn't do this step, you would end up with, we're about to end up with this, you would end up with that, which is not wrong, as long as you remember to put all your charges on there, including this one on the crowded carbon. Because this isn't wrong, it's just the charge-separated resonance form of a carbonyl. We just don't like them because they're more work to draw and ugly and represent reality slightly less. So, yeah, I was correcting myself there, but. All right, so now we've got this going on. And what we can do with this, make sure that I'm doing, okay, yeah. What we can do with this is we can go, hey, you know what? We have a negative charge here, but we already used hydroxide because this is base catalyzed. Base. You can do the exact same thing in acid, you just have to do enough proton transfers to keep everything positive. Try it at home for fun, see how it goes. But we can just go, hey, look at that water that's totally been sitting there forever. And I didn't just draw it because, I don't know, if there's water, it's all over the place, so why not? We're gonna appear that. Make it appear out of nowhere, and I'm going to go back to filling in my lone pairs that I'm not filling in. All right. This guy originally had 2 left, and he still has those 2 tiny little guys left. Yeah, I'm gonna draw the mini ones. I'm gonna draw one of them nice and like big, and then I'm gonna do tiny mini ones. Yeah. Yeah, and that's a hydrogen. So now we can do that, and now it's base catalyzed, right? Not base promoted, because base promoted is just the word we use when we're like, oh, I guess we didn't reform the base at the end. All right, fine, use a bunch more base. It's not catalyzed, technically. This one, we just reformed the base, so we are catalyzed. And we get those are gonna have to black light for now. And we start to realize why Leona sometimes offers, oh, and then that has a tiny little hydrogen. Why Leona sometimes offers to try and find her colored pencils to bring to exams, so that this whole mess of things that you're gonna have to slightly visually rearrange can actually be kept track of. If I can find my colored pencils, I will bring them to exams. I'm also gonna bring a bunch of like extra printer paper so you guys can just have tons of room, because I realize now I didn't leave a ton of room in your exam for you to, you know, do stuff. So we've made this. This is our aldol reaction. I'm gonna push it to the side for now because we're gonna use that in a second. We're not gonna do this twice. We're not gonna Your notes have the, where's it? Your notes have the acid catalyzed reaction in there as well. So you can try it using your base catalyzed reaction or mechanism that we just did. You can try to do an acid catalyzed version referring to this one, and then you can check yourself with the post-lecture slides that you'll get. So I have that in there. But, yeah, we've got another step, because we do this, and we get we end up with a carbonyl, and then alpha, beta. We end up with a beta hydroxy. So that's what we call alcohols when the whole thing, something else needs to take priority. So the whole thing doesn't get to be an alcohol, the whole thing gets to be a ketone, because that's more important. So this becomes a substituent, it's a hydroxy. So now we have a alpha, beta hydroxy ketone. These guys, it just sort of looks like more chemistry could happen, right? I don't know, maybe it doesn't, maybe it just looks like that to me because I'm very used to it. But more stuff can happen here because, I don't know, technically we still have alpha hydrogens, and we do have this, and I mean, if we can deprotonate, we can probably do some sort of chemistry. What kind of chemistry? Is it going to be useful, or is it just going to deprotonate and then nothing happens, so it protonates again? Maybe, but we have something that can act as a leaving group. So actually, maybe we can do further chemistry. Sorry, I didn't get rid of some of these. Oh my god, really? Okay, I feel a whole lot better about getting through these slides faster than the other chapter, because we have 86 slides right now, and there were 86 slides in chapter 18, which took us 2.5 days. Yeah, but we're about to have way fewer than 86 slides when I get rid of some of those join-in questions. So, once we get this guy, we can go, hey, that looks suspiciously like something that can turn into a leaving group. And, well, we would have to get electrons from somewhere, but hey, these protons are nice, this is, oh, okay, that's backwards. These protons and these protons are nice and, what did it do? Hold up, we have, okay, I drew our products correctly. Yeah, okay, this was our example that we drew. Our products are correct. They just jumped to a different thing. Okay, they drew a different thing, but we're gonna continue on from here and keep this one going. We can end up basically dehydrating. So if we take OH minus, which isn't a leaving group, but like, we can make it a good leaving group, and net, we end up from this specific carbon losing an OH with its electrons, right? An OH minus over here and an H plus from here, well, one of them brings its own electrons and one of them's just a proton. Put them together and you've got water. That's what we're losing from here, so it's a dehydration. This happens. So the KEQ for dehydration is generally large. Large KEQ means, so KEQ is products over reactants, right? So if we've got a ton of reactants and it doesn't make a whole lot of products, we've got a small number over a big number. Well, that gives us, that's a tiny fraction, right? So KEQ would be small. Yes, small number over big number, KEQ would be small. Products of reactants, if we have a large KEQ, well then, we've got way more products than reactants, right? Like several times more potentially. Or like a lot of times more. So that reaction pushes towards completion, and we actually most of that reaction goes forward, right? KQ for dehydration is generally large, which is why I got to here and was like, wait, we're done? Because yes, this is the aldol reaction, and what we're about to do is dehydration of an aldol, but like, if you did this aldol reaction, you should probably go ahead and try and dehydrate it, because usually that is very favored. Now, in order to get dehydration to like go forward quickly enough, because equilibrium will favor the dehydration, right? But it's not necessarily fast. So we're going to warm that up in either acid or base. And remember, heating doesn't change our equilibrium. Heating just gets us to equilibrium quicker. So we heat it up, give it enough energy to get where it's going fast, and then we get our products. And let's draw what we get from there. So, all right, I'm gonna draw exactly what we have, which means I'm gonna be more error prone, but you guys can correct me and it'll be fine. Oh, wait. That can go up here. This hydrogen can go away because I drew it there because it was the aldehyde hydrogen, right? So I drew it there because we had it drawn out nice and big over there. But now, we're gonna keep these color-coded, not actually because they're still electrophilic and nucleophilic, but because that helps us keep track of things, right? Since we're going to be doing this reaction right after this, usually, might as well keep everything nice and color-coded. So, first thing we're gonna do. Back up real quick. That's the stereo center, isn't it? This stereo center didn't start out as a stereo center, or didn't start out as with anything in a particular, like, it couldn't have been a stereo center because it was, where's our green? It was flat, right? And remember, anytime we attack a carbonyl carbon, because it's flat, you can attack from up here or down here, and you're gonna get a racemic mixture. So, that's a C hydrogen. That's gonna be racemic. And we're going to end up with, so when it starts on this page, it just reminds us, we've got this and it's racemic, so don't worry about drawing us stereochemistry there. All right. Let's see. We're gonna do, oh, wait, that's gonna go up here so that it's out of the way. Okay, we're gonna draw in these guys. I'm gonna draw in one nice and big. All right, this is still an alpha carbon, right? So these guys are still acidic. So we can take some of the, we're not gonna take water, we're gonna take base, because we can do acid or base catalyzed, and we already started base catalyzed, so let's do more base catalyzed. We can take some of this and deprotonate, and, well, that's why I was only gonna draw one hydrogen. All right, fine. The other hydrogen's gonna go over here, so it's way out of the way. There we go. That's gonna take this, and this is gonna go, it could try and kick up here, but remember, this one already has hydrogen, and if we need to draw that in, we can to remind us, but there's nothing really to kick off of here. I mean, we'd have to kick off OH minus, right? And that's not a leaving group yet. This, that's a really easy place for electrons to go, right? So, we get that. And there. Now there's only one hydrogen left, and it's over here. Yeah. And now we just protonated a hydroxide, so we can go, hey, what about the water that we just made? We can go ahead and unmake that water. And now we've done the steps that your slides don't show of the mechanism. Color coding. Here. Here. Now we've done the tautomerization that your slides don't show because they think it's cool to keep giving you half mechanisms because, well, we covered it on a slide somewhere, so it'll be fine. I don't like it. Now we've got this, and we've got this, and we've got hydrogen, that's a hydrogen, that's a double bond. And we did tautomerization, and now we've got an enol. So, that's what the chapter's named after, so we're probably going in the right direction to make something. Oh, okay. They have racemic under all of these because, well, if you start with a racemic mixture, you're not all of a sudden going to be able to take this mixture of half of them are oriented this way and half of them are this way and suddenly be able to select for one of them, right? Unless you're doing biochemistry, in which case you can have a really specifically shaped enzyme for that shit, but not with us. So, let's put color coding. So, your slides have racemic written under each of these, but I don't want to do that because that's not new information. All right, we made our enol. Now, what we're gonna do is acid catalyzed. No. Okay, well, your slides only have this dehydration. They have the example as acid catalyzed. We already committed to base catalyzed, so I have to use my brain more than I thought I would, which is fine, but I have this all printed out so that I can sleep 1 hour and come in and teach, and it's fine. All right, so now what we're gonna do is we need to make, I guess we just have to accept that we can make OH minus a leaving group in base, because it always, I don't like the rule that OH minus isn't a leaving group. Should we just do this in acid so that we're definitely doing it the way that the slides have, and I'm not fairly certain, pretty darn sure that we're good with what we're doing, or yes?
In the top left,
Yes.
I know we don't kick the bond to the one with the OH because it's got the hydrogen, but what if we kicked it to the right and then just immediately kicked that OH off? Wouldn't that?
So you could do that with arrows and that, you could do that and eventually you'll be right. It just won't be the actual mechanism, it won't be how it happens, because chemistry is all about just whatever. There's so many things that everything just sort of, it's not driving toward a reaction, things are just sort of happening, and usually they're happening in the direction toward I don't know, whatever's easiest, whatever's most stable. So breaking a pi bond, so you're not actually disconnecting two things, is always going to be way easier to do than breaking a sigma bond and kicking something off. And we know that this happens because of, you know, all the like labeling, oxygen labeling studies and stuff that we were talking about, how if you label one of the oxygens on a carboxylic acid or something like that, they're like, you realize they're interchangeable, and that's, that way we know that we don't just do nucleophilic attack and kick off the OH or the OH protonated. We do this and then come back down and kick it off. That way there's a step in between where they're indistinguishable. Same thing here. This is like, if I make you draw the mechanism, you need to draw how it happens, so this is what's gonna happen. But if you're using the mechanism to predict products, then yes, you can do that because that's just skipping steps in the mechanism, as long as you're keeping track of everything that's going on. Yeah, we're gonna break the rules and say OH minus, it's not a leaving group, but we're gonna say that that's a first semester rule, yes.
On the slides, it has the double bond between the alpha and the beta carbon, not the carbonyl carbon and the alpha carbon. Is that, like, I think that's what he was trying to say. Cause like, I understand that it should go to the carbonyl carbon, but they
Oh,
have to-
yes, that's products, we're gonna get there.
Oh.
Yeah,
awesome.
damn it. I got very distracted. Okay, just a second. Wait, today's a recitation day, right? Hell yes. Okay, let's finish this. Is that okay? And, you know, you have a quiz today? You have a quiz today, but I told him to make sure that no matter what he's doing at 30 minutes till the end of class, drops it, and you guys get the full 30 minutes on your quiz, so I'm just gonna steal some of his recitation time, and you guys can start recitation late. He comes in, I can just tell him, you guys still get a break between recitation and that. So, yeah, we're gonna finish this, sorry. Now, we are going to do, God, what's the mechanism of this? I'm sorry, it's so much easier when I just get to follow this because I can write out the step, and then once I write it out, I know what happens and I can explain it easily. Okay, we're going to do, what do you want me to do? That just does, okay. One of these guys reforms, and it's that, no, it's that one. Okay. Yeah, that one. Okay. So we get, yeah, because that one has this. Yeah, so, we're gonna do the hydrogen because, I don't know. Let's start with this guy. This is why I prepare ahead of time and have that's here, this is here, this is an OH, and that also has a hydrogen. Okay. Wish I'd paid attention to the fact that they only had one mechanism and I would have chosen the other one. So basically what's going to happen is you've got I think essentially what's going to happen is you can have more, what are we doing? We're doing reforming, no, we're not reforming that, we're reforming this one and kicking it off. Yeah, so we reform this, sorry. There's just the two alcohols and I can't do exactly what they're doing. Okay, we reform this because we really like to have a double bond, and this one we can't do that with because we drew in the hydrogen, right? I mean, we couldn't have done it if we didn't draw in the hydrogen, but we draw that in so the brain doesn't have to remember it's there, it's visually there. So this is the only one that can reform, and it really likes doing that because CO double bond is more stable than CC double bond. So this guy's gonna go scooch over there. Yes.
Do we deprotonate it?
Yeah, how do we,
Well, so this guy is not alpha at anything.
Not the OH
the OH,
one, because then it would be an OH, but then it would be like
It'd be-
positive oxygen.
yeah.
Oh. Yep. Thank you. Alright, that's this, and we can do. Now I know where the water comes from in a second. Thank you. This guy is gonna come in and steal this. This goes here, there we go. And we get there we go. Now we can form this because we're in base. When we form that, that kicks over here. That kicks this over here. And wait a minute, we're trying to kick pi electrons over to here, and this has already got 4 bonds. But we do have something that kind of works as a leaving group. So I know in Outcome 1, OH is not a leaving group. In base, it gets to be a leaving group. If something is acid or base catalyzed, and this is what we need to end up happening, then like, we're not gonna protonate that. We're not gonna have a protonated alcohol in base, so this is what ends up needing to happen. Then we get that hydrogen that was always there. We have OH minus leaving, which can then go, we just form the water over there so it can go, hey, what if I stole your, what if I stole your proton and you were the OH minus? Not that that's gonna have any difference because, you know, you're starting with water and OH and you're making it. But now we've got this. That. Now we've got this going on. And the 2 carbons that weren't bonded together at all before are now double bonded together because, well, there was going to be a carbon-carbon double bond anyway, and this way we get to have a CO double bond, so that's better. Yeah? Does this kind of make sense? Sorry that this was not what I had pre-planned, so you got to see me think live and in person. But yeah, if you go through try going through that part of the mechanism, or that whole separate mechanism, in acid, because there is a thing you can check it with, and then once you do that, try this next step with acid, and maybe it'll make more sense since you have something to refer to for this one in acid. Okay? Sound good?